Teaching Rotation with the Meter Stick Torque Set webinar. I'm Dan Burns. I'm the physics curriculum and training developer here at Pasco. Before that, I taught high school physics in the San Francisco Bay Area for 27 years. And so hopefully I can share some of the things I've learned here at Pasco and over my teaching career with you today about teaching rotational dynamics. My job description, well, it's maybe a paragraph or so, but I can summarize it as help physics teachers. And there's my email there, dburns@pasco.com. If there's anything I can do to help you, especially with labs, troubleshooting, ideas, things like that, feel free to contact me anytime. I'm joined today by our training manager, Glenn Starkey. He's working the cameras and all the other equipment. And also our sales engineer, Brandon Pruitt, who's going to be manning the chat and the Q&A. We are recording this session, and so you'll receive a link to this recording. Before we get going, just a few housekeeping things here. Can you get the recording? Well, you'll get a follow-up email, which will have a link to it in like a day or two usually. If you're interested in a professional development certificate, there will be a link to a quiz in that email, a 3-question quiz that if you watch this video, you should be able to easily answer it. If you need help, let me know. And I think you get the certificate if you get 2 out of 3 anyway. But pay attention, it'll save you some time. And if you would like a copy of these slides and then the files for the labs, and I have data files and things like that, there will be a link to that in the follow-up email as well, and we'll be seeing it in the chat, and it's on the slides too. If you get the slides, you'll pretty much get all the links that we'll be talking about today. We're using Zoom Webinar, which has a Q&A panel, and so I recommend you use that if you have questions for us, because it puts them in a queue for us to answer rather than in the chat. Sometimes the chat will scroll by and we might miss a question. And so I would use that. If you need captions, just click on the live transcript and select that. If you're going to use the chat, and I recommend you do, I'm sure there are things you have to share about what you've done with these topics, or if you want to comment on something else somebody else chatted about, use the chat. But make sure you change the default is hosts and panelists, change that to everyone, at least if you want it to go to everyone. I always forget to do that, and I'll send something to everyone, and then it only goes to the hosts and panelists. And so that's how you would change that. So our agenda today, I'm going to talk a little bit about the meter stick torque sets, and then we'll be looking at 3 different labs, and we'll also bring in some other Pasco equipment, some sensors, the wireless smart gate and the wireless rotary motion sensor. But you'll also see a lot you can do with just the meter stick torque set. And there's that URL to the slides and the files we're going to be talking about. So the meter stick torque set, you can see all the stuff that comes with it. One of the most important parts is this pivot that's has 2 bearings on it, and I've attached the meter stick clamp to it, which has a little bubble level. And then on the back side is a 3-step pulley. We're not going to use that in this first activity. It really wouldn't matter, but I take it off if I'm not using it. We'll use it in another activity. And I'm just going to attach it to the rod stand. Another thing to see is there are 2 holes you could use to attach it to the pivot. And I have picked the one off center. And so that helps if you're doing balancing experiments, because when I attach the meter stick to it, you're going to see the bubble level on top. You're going to see it comes to equilibrium a lot easier. And so it makes balancing experiments easier, quicker, more accurate. And so I got it at 50, stays balanced pretty well. Now this meter stick, well, I should have shown you this before I took it off, put it on there. It's made out of aluminum, so you saw it balanced right in the middle. It's very highly precision made. It's hollow, so and it's aluminum, so you could actually do a lens law demo with it. And what some people have found is you can do it on the outside so students can see. Does it reach terminal velocity? Well, that's a whole other webinar. So just a teaser there. Let's get it back on there. So meter stick, aluminum meter stick is one of my favorite new things. And I should have mentioned this meter stick torque set was a winner of the Best in STEM award in 2022 in this year. There we go. Other things, we have 3 mass hangers, and the mass hangers are labeled with their mass, 10 grams. And there's a bar to hang mass on it. There's even a little scale that you can use for angles. That won't come up in today's labs, but it can come up in some of the other labs that we have for this. And there's a little hook here if you want to hang something on it. And if you want to look at the 7 labs that we have posted for the meter stick torque set, on the product page, there's an experiment panel that will show all those labs. So let's go on and do something with it. So the first lab I'm going to show you, there's no electronic sensors or anything. It's just doing a balance lab. This is maybe a step up from a basic torque lab that you do where students would just balance 2 things, keeping the meter stick in the middle. This one, we're going to move a little bit past that. We start out with something like that, but then we get more complex with 4 little torque puzzles, I'll call them. And each one is a little bit more challenging than the previous one, and they're all independent. So you can pick and choose which ones you want students to do, or it's a good way to differentiate your instruction. You could assign one puzzle to one group and another puzzle to a different one, and then have them present to each other. So this first one, I'm going to put a mass hanger at 90 centimeters. And from this, we're going to hang an unknown mass. And so I'm going to be using our hooked mass sets. So I picked the tray that the masses come in as my unknown mass, but this could be anything, but something that offhand students wouldn't know the mass of. You wouldn't want to use a standard mass. And then I'm going to balance it on the other side with a known mass, 200 grams. So the total over here is 210. And I just keep moving that guy until I kind of know where it should end up, but it's pretty easy for students to find it. And the bubble level makes it real easy to see if you have it precisely. You may even have to tell students, hey, if you're within a millimeter, that's pretty good, because they really like to be perfect sometimes. So that's pretty good. And so I have this at 26.5 centimeters. And then this guy's at 90 centimeters. And the pivot's at 50. So we can use an equation, the sum of the torques equals 0, to calculate this unknown mass. And I'm just going to do it real quick here. So this lever arm would be 50 minus 26.5. And I'm using centimeters. And then this is 210 grams. So I multiply that by 210. I have the torque here and leaving G out, but I don't do that in the next slide. We'll see. And then over here, I have a known lever arm, 90 minus 50 or 40. So I can divide that by 40. And it tells me the mass is 123 grams, but that includes this 10 gram hanger. If you didn't want to add that complexity, you could just hang it by the string on the meter stick. So that says it's 113 grams if it's just this. And there we go. And it's 112, off by a gram. So that's pretty good. And so what's another thing I like about this lab is the students don't wonder, gee, are we doing this right? As they go through it, they find out if they did it right. And so if they don't have a really accurate value for the unknown mass, they need to try again. And if they had an accurate one, they can go on to the next part. The second one, what we're going to do is see if we can figure out the mass of the meter stick. Now, the mass of the meter stick didn't matter in this one we just did, because not for torque anyway, because I had it at the pivot. But what if I put it off center? I'm going to move it to 75 centimeters. And so now it doesn't balance. But if I hang a known mass over here, depending on what I pick. So a lot of the numbers and things that are used in the lab are somewhat arbitrary. So if you adjust them, just make sure it works. So if you don't have enough mass here, you're never going to balance it. And this sometimes, this is a pretty challenging torque puzzle for students. They just look at it and they're like, well, what's balancing it over here? Well, we know it's the mass of the meter stick, which can be thought of to be concentrated all at the center of mass at the 50 centimeter point. So I can do the sum of the torques for this, and the unknown in this case is the mass of the meter stick. So this lever arm times the force equals this lever arm, which I know is 50 minus 75 times the unknown mass. So just real quick. So that's at 92.3. Forgot what I got last time. And then again, the mass is 210 grams. And then divide it by the 25 centimeter lever arm here. And that's not right. What did I do? Oh, 92.3 minus 75. And I get 145 grams. So the students can check that. And oh, it's 146. So again, off by a gram, but very accurate. I've done this lab without this equipment, with just strings and things like that, and it works pretty well. But when you get things within a gram, it makes it much more likely the students are going to be careful. They know they can get good answers, and it's much more likely they're going to realize the relationships are supposed to be seen here. The third puzzle, well, I'm going to go to the next slide here. And so this is in the teacher's guide for this lab, which you can get access to if you go to the Pasco website and sign in to your teacher account, which is free. So if you don't have a teacher account, you just make one and we'll verify that you're a teacher. And that would give you access to the teacher guide, which has the answers to everything here. And so this one's a little more complicated. In this case, we're going to put the pivot off to 30 centimeters. And we're going to put the 210 mass at 5 centimeters. And what they're supposed to do is predict where to hang the 50 gram mass, a total of 60 grams with the hanger on this side to balance it. So in this one, they calculate first before they balance, and then they decide where to put it. And so in the equation here, when I solve for that unknown, I got 68.5 centimeters as the location for the 60 gram mass. So this is the part the students would do after doing that calculation. So I'm just holding it. It's not released yet. Let go. And boy, that's just satisfying to make a prediction like that and see even the bubble level is saying it's exactly horizontal. And so students get excited about that. This is one of the more challenging ones. The last one also, students can get puzzled by it. But if you're studying center of mass, this is a good one for them. And so what I'm going to do is attach an unknown mass to the meter stick. Well, the tray worked pretty well for that. So we'll use it again. But you could use a different unknown. And then I'm just going to tape it securely to the meter stick between 0 and 30 centimeters. Securely, because you don't want it rattling around. It doesn't have to be an entire roll of masking tape to hold it. That's pretty good. I might add I'd tell the students to add another one. But so what I'm going to do is hang it. So the pivot is at 60 centimeters. And again, some of these values are somewhat arbitrary. You may have to adjust that for the unknown that you decide to use. And then I'm going to take the 210 gram and find where it balances. So my job is to calculate where the center of mass of the meter stick mass tray combination is. It's not two things now, it's one thing. And they know the total mass of it. They solve for them individually. Down here, you can see the total mass is 0.262 kilograms. And so what I know is the mass over here, or the weight, if you want to get the torque, is located at some unknown position, the center of mass. So there's an unknown lever arm I'm solving for. I know the lever arm and the mass and weight over here. So this torque equals the known force times the unknown lever arm. And in this case, it comes out to 37.2 centimeters here, but I tape this on, it's going to be different. Let's see if I can do that live here. So that's at 60. So this is at 90.3. So the lever arm here is 30.3 centimeters times the known mass. And then if I divide by the mass of the meter stick tray combination, it tells me the lever arm is 24.3 centimeters, but I have to subtract that from 60 to get the location on the meter stick, right? So it says it should balance at 35.7. So now I take this off. So this is what the students would do after they calculated where it should be. 35.7. Oh, we're off. I did it a little quickly there. This might have moved a little, but if you actually then balance it, you'll find I was just off by a couple of millimeters. So it's, if they get within a half centimeter on this one, that's pretty good. So it's not quite as accurate as the other ones. So that's the gravitational torque lab. Let's move on to the next thing here. When I did that in class, they were required to remove all tape before they left the classroom. Otherwise, you end up with tape all over your meter sticks. So this one I put together ahead of time. You don't want to watch me fiddling with it, but the diagram that's in the lab is pretty good. We have our pivot from the meter stick torque set, and I do have the 3-step pulley attached on the other side. And I tied a string to the 3-step pulley. There are little holes in it. And that string comes out and over a pulley that's going to be attached to a hanging mass. And we'll start out with the hanger's 5 grams, so I'll add 15. And so we'll start out with 20 grams on it. And so so we can wind that pulley, the 3-step pulley up. You have to be careful, there are 2 pulleys in this experiment. And so now this is going to apply a torque and make this spin, but that's going to be pretty fast. Let's put the meter stick in the clamp to slow it down. And I'm going to put it right at 50. So now what I can do is measure the acceleration of the mass or the angular acceleration of the meter stick, and then calculate the torque based on the other measurements and that measurements. And we can figure out what the relationship is between torque and the angular acceleration of the meter stick. Now, attached to the pulley, I have a wireless smart gate. And so I'm going to set it up to measure the angular velocity of the pulley. Well, that string is going over that pulley, so its angular velocity is going to be the same as the angular velocity of this other pulley, which is also fixed to the meter stick. So indirectly, the angular velocity of the pulley is the angular velocity of the meter stick. And so if I get the slope of angular velocity versus time, I get the angular acceleration. So it's a pretty common lab, all kinds of ways to do it. This one works really well. And so I'm going to bring up our SparkView software. SparkView is a app you can get for your tablets and phones in the App Store or the Google Store, or and also Chromebooks, the Chrome Store for free. For PCs and laptops, there's a single user or a site license fee. So what I need to do is set this up. I do have files all set up, and I even have a file with data in it that we'll use, and I also posted those. But just to give you an idea how you might go about setting this up yourself, first thing I want to do is connect to the smart gate. There's the power buttons underneath. So I turned it on. So now it is ready to connect by Bluetooth. So we go up here. And the Zoom stuff is getting in my way. Hang on a second. The SparkView showing. Yep. And so the Bluetooth, I want to say build experiment. And what I'm going to do is have a graph and then a data table to save some of the things we measure. And up here, I connect. It should see the wireless. There we go, smart gate. So I just click on it. And the smart gate, I'm not going to go into it. I have a slide about it up there, but it does a lot of different things. We're using it with a pulley. And so sometimes it's called a smart pulley. So if you go to smart gate only down here, it's one of the choices. If I did smart pulley linear, it'd measure the linear speed of the outside of the pulley, but we want rotational. At least that's what I'm going to do. And then I have to tell it the angle between the spokes on the pulley. And so the pulley has 10 spokes, 360 degrees, 36 degrees between spokes. That's the default. And so our graph is going to be angular velocity. This just says velocity, but notice the units are radians per second. And so that's our graph. And then the data table Well, what I'm going to vary is the mass on the hanger. So I'm going to start out with 0.02 kilograms and increase that by 0.02 kilograms each time. So let's make that data column the hanging mass, I'm going to call it. So it's not a choice here because that's a user entered one. So I click user entered. I can create a data set or a calculation. We'll see what a calculation is later, but this is just a data set. I'm just going to input some numbers and I give it a name. A mass, give it units, kilograms. There we go. So I can put in my values. I'm just going to collect one data point here, and then we'll look at a whole set of it once you see how that works. And then this other one is going to be user entered. And it's going to be the angular acceleration. Now that could get confusing because the smart pulley also measures angular acceleration. It means the angular acceleration that goes with that particular trial. So we do have to create that, and then radians per second. And this is something I learned just recently. Over here, if I want to put squared, I select the little Greek letter icon and shift, and then I can get squared. Always learning new things here. Although per second, you could argue that's even a better thing. So let's see what that looks like. So let's wind this guy up. If you're doing this in class, you know, you probably wouldn't put it at eye level, but we're interested in you being able to see it on the camera well. So I'll be very careful here. And so I just hit start and release it. You should be seeing data. There we go. And I'm going to hit stop just before it hits. And stop that guy too. And I can hit the auto scale button. Oh, it got me. And you can see it's a pretty straight line. What I found is the air resistance affects the lower mass trials a little bit more. It seemed wrong to me because it goes faster for the higher mass ones, but compared to the amount of torque being applied, the air resistance is more of an effect at the lower torques. So I want to get the slope of this. If I just click the linear fit tool, it's a pretty good slope. But if you wanted to get a little bit better, I'm going to pick the select tool and just select the part before I think air resistance started to slow it down. And it's usually pretty easy to see. Another option you could do is, well, do heavier masses or not let it fall as far. It doesn't need to fall this distance. And so I get a slope of 0.352. So what I would enter that. And then we would collect, well, 5 or 6 more trials if you want. The mass set I'm using, the Pasco hanging mass set, mass and hanger set, I guess it's called, has 6 20-gram hangers in it, or masses in it. So I could do 7 trials if I wanted to. And I think in the data file I did. So once I got those trials, now I want to make a graph, but I need to figure out what the torque is. So what I'm going to do is do that on another page. So I'm going to add a page. And in this one, the data table is going to come first. We have to figure that out. And the graph will come second. So the torque is from the string pulling on the 3-step pulley. And so that is the tension in the string. It's not the weight of the hanger. That's the torque on the system. And you would have to include the rotational inertia of the hanger. It has some. That's another approach. Most people don't do it that way. So the torque is the tension in this. So students would have to solve for that with a free body diagram. Tension's up, weight is down, the acceleration's down. So mg minus the tension, I have this on a slide too, equals ma. So if you solve for the tension, you get it's the mass times g minus a. And so I'm going to say select measurements. And I'm going to say user entered, but this is a calculation. So I'm going to calculate the torque for each of the hanging masses, or tension in this case, first tension. You could just go right to torque if you want. So tension equals, well, I said it was the mass, which is a measurement, user entered, hanging mass. So that'll go and grab the mass from the table, and then times parentheses G minus, well, the acceleration of the mass is equal to the angular acceleration of the pulley times the radius. And the radius is 2.4 centimeters. So I want to multiply the angular acceleration by the radius. So that'll give me the tension. I'm not going to bother putting the units in here. They'll do it for the next one. So now notice it's calculating the tension. And then I know the torque is the tension times the radius. So I'm going to enter a calculation for that. So notice this calculation shows up, and it's mad at me for not putting in the units, but I'll do it for this one. Create edit calculation. And so I can just hit enter and put it on the line below. So torque equals, well, it equals the tension. So that's a measurement now. Whoops. Oh, that's okay. That's a measurement, tension times the radius and if you want to do the units, you can do it later, but if you click properties and edit the units, you can put in this case, Newton meters. So at least our graph will have units. And I just hit a bunch of OKs. And so now it would start graphing that if I pick torque versus angular acceleration, but again, not picking the angular acceleration from the sensor, but the one we measured from our graph. So I'm going to open up a file that has all the data there. That's pretty much, hopefully, exactly what I did here. So these two files are in the Google Drive we shared with you. No, I don't want to save it. So you can see here I collected 7 data points. So I did use all the 20-gram hangers. And then we have our graph of all the data for torque and angular acceleration. And the slope we know is the rotational inertia of the meter stick. So the students have already calculated that using the 1/12 ml squared equation. And then they compare it to this, and it compares pretty well. They also compare the units. They're both kilogram meter squared, and their y-intercept is very small. And so y equals mx plus b. So they get torque equals I alpha. So this slide just summarizes all that analysis. Here's our angular speed. Here's how you figure out what the tension and the torque is, and the radius of the pulley. You can have the students measure that if you wanted to. And this is data for a different time I went through it. But here's the comparison. The calculated rotational inertia, 0.0123, and the slope, 0.0133. I forget what it was on that SparkView file, but it's similar. And so rounding to the nearest thousandths, 0.013 versus 0.012, that's pretty good. Then the students are asked to do an extra prediction. How much time will it take a mass they haven't measured to fall to the table? And so that's what that last part is there. They develop an equation for the acceleration of the falling mass and predict the time. And my students would get pretty excited about that because it kind of falls slow. Let's say they did it for 25 grams. That's one they didn't test. And they'll make some sort of prediction and they're up, it came off the string. And then they release it. It takes quite a while to go. And that also brings up another way you could do this lab. You could do it just with the meter stick torque set and the pulley. Students can measure the time it takes to fall and measure the distance and calculate the acceleration because the distance is 1/2 AT squared. The only thing is if it falls kind of fast, it's not going to be very accurate. So if you're going to do it that way, maybe add instead of 20 grams each trial, 10 grams. If you tried it out, you'll find you can get pretty good with the stopwatch. So that is the Exploring a Rotating System lab. Any questions coming up or are we good? So let's move on here. So this next one, still featuring the aluminum meter stick, but I'm not going to use the pivot. I am going to use the meter stick clamp. I'm going to use our wireless rotary motion sensor. And the rotary motion sensor works like a pivot, except it also has a device in here measuring directly the change in angle as a function of time. So it can also get the change in, it can get the angular velocity and the angular acceleration. And so we're going to do kind of a more advanced sort of a lab here. The first lab, a regular physics, maybe an honors physics would be doing that. The next one, maybe honors physics, AP Physics 1, AP Mechanics C. This is more of an AP Mechanics C college level lab, the falling beam. So I'm going to just attach this to the stand and I'm going to put the meter stick so it's all the way on the end. And you might say, wait a minute, how is it going to attach to the end? Well, you can get pretty darn close if you look at where the end of the screw is and have it so it's right on the end of the meter stick, but all on, well, it's maybe at 1.5, maybe 2 millimeters from the end. I don't think you would notice that in your calculation. So I would just tell students, assume it's on the end. I'm going to put this here as a cushion because what we're going to do is release this from a known angle and measure its angular velocity as it goes through horizontal. And the students look for a relationship between those quantities using their physics. So let's go on to that. Oh, just wanted to mention there's also an accessory kit for this, a rotational inertia accessory kit with these two things then together. It's a full featured rotational dynamics lab. Comes with, if you're looking at the slide there, that bar with the masses on it can do what the meter stick just did in the last lab. So you can do that last lab and adjust where the masses are. I meant to mention you can put these guys on the meter stick too if you want to change its rotational inertia. It's measurable. So a little plug for the accessory kit. So this is what it looks like. I can lower this somewhat. You just want to make sure it hits the box after it's gone through horizontal. And so that's the setup for this one. And what I want to do is collect data for different angles. I'll start off high. Oh, just look at how close that comes with the camera. Or start out high, a large angle, and then decrease it as we do the lab. But again, we'll just do one data collection and then show what it is with a full set of data. So the basic idea here is you're going to use conservation of energy. And so the potential energy of the meter stick. We're going to release it from rest, the gravitational potential of the meter stick Earth system, if you like, is equal to the kinetic energy, the rotational kinetic energy of the meter stick when it's going through the horizontal, or really any point, depending on how you define gravitational potential. So I need to know the change in height of the center of mass of the meter stick when it falls. So if I released it from vertical, the center of mass falls 50 centimeters. If I release it from some other angle, then the change in height is going to be 50 centimeters times the sine of that angle measured from the horizontal. And so that's really one of the trickier parts there. So let's see, we use Spark View. Let's use Capstone. I'm going to quit Spark View. Oh, look at the, so look at our slope was 0.0129 compared with 0.0123. So this one even worked out better than the data I have on the slides. So Capstone, everything, I could use SparkView again. Doesn't really matter which one I use, but Capstone has more features to it. You might find it easier to use, but more features also can mean more things for students to have trouble with. And so it's up to you. It doesn't work on Chromebooks or tablets or phones. It only works for desktops and laptops. So it's tend to be used more by colleges, maybe AP Physics, IB Physics classes. But since this is that level lab, I thought it'd be appropriate to use Capstone. So I turn on our rotary motion sensor and connect to it. Just like we did with SparkView, it's just the process is a little different. Oops, SmartGate, I didn't mean to do that. Why didn't it see that? Oh, I just wasn't patient enough. So it sees any Bluetooth device that's around, and I didn't turn off the SmartGate. That wasn't smart. No, they turn off by themselves if they're not connected, and that helps save batteries. They're rechargeable batteries. So what we want is a graph, actually two graphs. So I'm going to add a graph to the same axes. So this button right up here gives me a second graph where they share the same x-axis. And the first one, I'm going to graph angle. And the second graph, I'm going to graph angular velocity. And we can make that a little bigger. And then in my data table, I'm going to record what the initial angle that I released it from was and what the angular velocity when it went through the horizontal was. So this works a lot like SparkView. I just click on that and I say create new user entered data. And so I'm going to call that initial angle. You can put theta if you want in there. It'll be quick. And then for units, radians. You could use degrees if you want. I'm going to use radians. And then versus the angular velocity, but it's not any old angular velocity. It's the angular velocity when it's horizontal. So you can call it the final angular velocity if you want, but it is a new data. I'll say final omega, right? I didn't do omega, but kids always call it W anyway, right? So now I'm ready to collect data, but for the high angle parts, when it's going through the horizontal, it's going pretty fast. And if I want better data, I want to collect at a higher data rate. So down here, the default is 20 Hertz. I'm going to raise that up to 200. You could even go higher if you want. 200 works, as we'll see, but I'll leave that up to you. Now, here's the tricky part. I want to know how fast it's going at 0 degrees. Well, it's not that tricky. When I start recording, wherever the meter stick is will be 0. That'll say that's 0 degrees. So I just look at this bubble level, raise it until I see it level, then I start recording. So that point is 0. So I lift it, and I'm watching the angle graph. And when I see it near an angle I want, I release it. And so the way you release it, you don't want to be holding. Well, I guess you could, there's a bunch of techniques that would work. What I do is hold it from below, and then I move my finger quickly directly away from the meter stick. So I'm not jerking it or anything, but usually with the release is not a big deal. Students can do it. So here is the angle, and I want to know what the angle was before I let go. So up here is the multi-coordinate tool. You can also use the coordinate tool. I like the multi-coordinate tool. So wherever I move that, it tells me the y values on both graphs and then the x value down here. So I find when it looks like it first started to move, and the angle there was 1.436 or 1.44. It is pretty accurate, but probably not quite that accurate. So 1.44 is good. And then the final angular speed, well, remember the trick we did. When the angle's 0, that's where I want the angular speed. So the multi-coordinate tool makes that real easy. I just move until I see that it's on 0 up here, and then I read off the angular velocity down below. And so I'm pretty close, negative 0.047. I don't know if you can see that, but if I go down here, I can nudge it and see if that's as close as it gets. Oh, 0.019, 0.009 positive. And so because of the data rate, that's as close as we're going to get to 0. That's pretty close. And so 5.34. It is negative because of the way I have, I could change it. So default is clockwise. But when it goes clockwise, that's negative by default. So you can have it rotating the other way, or students can change the sign of the graph pretty easily. But it doesn't matter. It's angular speed is what we want. So then I would do a second trial. I won't measure it, but I'll just real quickly show you how fast the data collection goes once students get the idea. So I hold it level, hit record. So now I have 1.44, so maybe about there. You can create a digits display instead, but you just keep doing that. And so I'm going to open up a file I've already made here. This falling beam. And I do have SparkView files for that as well, if you wanted that. And so this one is just for the webinar. I took out some of the last steps so I can show you, walk you through them. So you can see the same thing that we just did, except I've done it 8 times, and I have the angular velocities recorded. So we went through how to do one of those, so the students would go through and do more. And getting 8 points doesn't take very long. And what I'm going to do is add a page. And so I can click on this little icon. If I do a mouse over, it says that's add page, or it's a workbook page. So I go to workbook, I can say add page, either way I get it. And then I can create new things here. Well, what we want is a graph. So you can just double click on the graph here or drag it over. I think I dragged it over last time. There we go. And so let's see what our angular velocity versus initial angle looks like. And again, it's the final angular velocity, the one we made, and the initial angle. And we see it's not a linear relationship. Now I know the kinetic energy is related to the angular velocity squared. So maybe we need to graph angular velocity squared, and Capstone has a feature that makes that pretty quick to do. I just click on the axes and I go to, well, it's called Quick Calc, and I can do any of these really quick, like changing the sign. You could do that for the angular velocity on the previous, but I'm going to square it. So now it says final angular speed squared. It's not straight yet. And so the students, because they figured out the height is half the length, the change in height is half the length times the sine of the angle, maybe we need to try sine of the initial angle. And they'll know because they'll have an equation that they developed. It's not one of the quick calcs. So for that, I go over to calculator and I have a new calculation. I'm going to call that sine angle. And down here are different functions. I'm going to pick sine. And then the measurements, maybe SparkView is a little easier to see this, but in Capstone, the icon to say data measurements is this little rainbow triangle. And so if I click that, I can see my initial angle shows up here. And then this trips me up a lot in Capstone. Watch whether it's degrees or radians, it defaults to radians. So it sort of got me used to, hey, I'm in Capstone, I'm going to use radians. I'm not going to burn myself again, but you can change it here. You can toggle between degrees and radians. So just watch that. And there's no units. So I'll just delete that. Unit is dimensionless. So now when I go here, sine of angle shows up as, oh, did I do something wrong? No, there it is, as a choice. And we can see it's pretty straight. I don't like these connecting lines for a lot of physics things. So if I right click on a point, I can turn it off. And then I can go up here and do a best fit. And it looks more linear when I do it that way. And so the slope is 27.4. So how do I know what that means? Well, again, this slide, a lot of stuff on here because it's just summarizing all the analysis, which is in the teacher guide. But here's the data. The students using conservation of energy developed this equation. Omega squared is 3g over L times sine theta. It's really also, if you say that's sine of the change in angle, that it's true for other cases, not just the horizontal position. So if I graphed the angular speed squared on the y-axis and sine theta on the x-axis, the slope is 3g over L. So you could have them use the slope to find g or to find L, but by this time they're in the class, they know what g is, and finding the length of a meter stick, that's probably something they're not going to do. So I just have them calculate the theoretical slope as 3g over L, and it's 29.4, and we came up with 28.7. The units are 1 over second squared, same as the units on my slope, and so they can see, hey, that it worked. And then as a final challenge to them, I ask them to predict what the angular velocity would be if I release it from 1 radian and when it's going through 0.6. And they might think, oh, that's a whole different problem. Well, the answer turns out to be pretty much the same equation, except it's the, I think I said over here, it's a change in angle. It's the sine of one angle minus the sine of the other, not sine of the change in angle. So it's just a little bit more complicated. And when I did this, I got a predicted 2.85, I got 2.83. So that's the kind of accuracy you can expect when you're using Pasco sensors with our either SparkView or Pasco Capstone. So again, that's the URL for the files. That is the end. I thought we'll let you out early today. Also, if you're interested in learning more about any of the equipment you saw here today, including the Best of STEM 2022 winner, the meter stick torque set, use that QR code to contact your rep or go to the Pasco website and you'll see a place you can use to find out who your rep is. Highly recommend talking to your rep before any purchase here at Pasco. They will fix you up. Any questions or anything, Glenn?